The next topic in this section introduces this new theorem, which is what we're calling method of proof by division into cases. This is still a direct way of proving things, and we use this method when we have conditionals of the form if A1 or A2 or A3 or so on and so forth, then C. So in other terms, if you have a conditional statement with an if-then form, and your hypothesis is made up of multiple cases that lead to the same conclusion, we use this method of proof by division into cases. Now, how do you prove that particular conditional? Well, the way you would do it is you would isolate A1 and you would show that A1 gets me the C. And then you would isolate A2 and you would show that A2 leads to C. And so on and so forth until you've done all the possible cases. This is the reason why we call this method of proof by division into cases. You're breaking the original conditional down into multiple conditionals and proving that each one of them is actually true. If you can prove the statement is true the first time, the second time, and so on and so forth, then you have proven the conditional is true in general. So let's take a look at an actual example. It says, prove that the square of any odd integer, n, has the form 8m plus 1 for some integer m. How would you go about proving this? If you thought to yourself, I'm going to start with an integer that is odd, then you could start with 2k plus 1, for example, and you want to prove that the square of it has the form of 8m plus 1. You might be tempted to square this, which would be fine. You would end up with 4k squared plus 4k plus 1. And you would notice that the first two in this list have a 4 in common, so that could be factored. You may end up with 4 times k squared plus k inside parentheses plus 1 on the outside. Now the problem with this is it is not the correct form. They wanted 8m plus 1, where m is an integer. You ended up with 4 times m plus 1. So this did not really work out for us. So what would we do instead? So, well, we're going to prove this in a slightly different way. We're going to start with an integer n, and we're going to suppose that the integer is odd. And keep in mind that we want to show, that's what WTS stands for, we want to show that the square of the integer, meaning n squared, has the form of 8m plus 1. Now, originally, when I did that kind of on a scratch paper and I just squared the 2k plus 1, I didn't get the right form. So it turns out that the trick here is to divide the original number by 4. And keep in mind, because you're dividing by 4, what could happen? Well, the quotient remainder theorem says you're going to end up with some quotient, in this case I'm calling that quotient k, and some remainder that I'm calling, in this case, r. Keep in mind that r is a special number that is between 0 and 4. Now, not all the remainders can be possible. Some of them lead to some crazy nonsense, and some of them could be legit. So I'm going to try to isolate which remainders lead to nonsense, and I'm going to ignore those cases. And I'm going to look at the rest of the cases and see if they give me the correct form that I'm looking for, which is 8m plus 1. Now, the remainders are 0, 1, 2, and 3, and automatically we can eliminate a couple of them. Since n is odd, we can automatically eliminate two choices, 0 and 2. Why? Why can we eliminate 0 and 2? Well, because if the remainders were 0 and 2, then think about it. The n would be 4k plus 0, or in the other case, it would be 4k plus 2, which would imply that it's even in both cases. So again, if the remainder is 0, then n is 4k, and 4k can be written as 2 times 2k, where 2k is an integer. That makes n even. But remember, we suppose that n is odd, so this case cannot happen. And the same thing will apply when the remainder is 2. That means that n is 2 times 2k plus 1, and 2k plus 1 is an integer, so that means that n is even by the definition of even, but remember, this cannot happen. We had originally started with an n that is odd. So the case 0 and the case with the remainders 2 are automatically eliminated. The n is supposed to be odd. So there remains two cases, the 1 and the 3. And that's what we're going to look at next. What would happen if the remainder is, for example, 1? Well, if the remainder is 1, then my n would have the form of 4k plus 1. Keep in mind that this is still an odd number, it's just not the definition that we're used to. So when I square 4k plus 1, I'm going to end up with 16k squared plus 8k plus 1. And the first two terms in this list both have an 8 that can be factored, leaving me with 2k squared plus k, which is an integer because k is an integer. So that's exactly what we wanted. We wanted 8 times some integer plus 1, and we got that. Now what about when the remainder is 3? Remember, that was the last possible remainder. In that case, my n is going to be 4k plus 3, and so when I square it, by foiling the parentheses, I get 16k squared plus 24k plus 9. Remember, ultimately my goal is to make this whole thing look like 8m plus 1. So what I want to do is break the numbers down into multiples of 8 if possible. 16 is already a multiple of 8, 24 is already a multiple of 8, but 9 is not a multiple of 8. So I have to break the 9 up into 8 plus 1. So that's what I did on this line. Again, why am I doing this? I'm doing this because now the first three terms in my solution all have an 8. That can be factored out. And keep in mind that the k is an integer, so the whole thing, 2k squared plus 3k plus 1, is now going to be some random integer. So therefore, my answer is 8 times some integer plus 1, which is the desired form. So in both of those cases, we got the right form that we were looking for, so that means the theorem is actually in fact true.